Boom. Okay, and we are recording now. So where we left off was talking about the broad details of the indexing process. So the indexing includes three kinds of servers: index servers, document servers, and spelling servers. And we'll cover each of those. Essentially what happens, the basic process, user enters the query. There's going to be one stage where the query gets routed off to look for alternate meanings for the words. For example, if you typed in something that was a little off, Google will basically do a kind of autocorrect on that and say, hey, maybe you meant this, not that. So that's what the spelling servers handle. The index servers, they're the parts that look up the various pages in the index corresponding to your search terms after it's been grouped, and they bring all that together. The document servers themselves, that's where the web pages are stored. So that's pretty much it. That's the whole system. Now, most of the time for a query, the indexing process is not going to look at the entire document. It would be really, really slow if every time Google did a search, it had to scan the entire document. They could not deliver the results in half a second at a price of nothing. So instead, the document servers store the actual web document data, but it gets basically purified into some kind of database form where Google has all the specific things that it uses to do the ranking. And that's what the index servers actually look at. So anyway, let's go on. So first thing, index servers. So they're grouped into clusters and divided by language. Now, that means typically at different data centers, you're going to have one dominant language. For example, data centers in the US would be overwhelmingly English language, but you go over to Europe, right? And in Europe, you could travel 100 miles and be speaking two different languages. So for that, it makes sense that they have one big data center and they're going to have that partitioned off by languages. So anyway, however many search terms there are in however many languages, each of those search terms gets associated with a certain number of pages, quite often large. So example we saw the other day, if I had to search money, it shows up on some 4 billion pages. Anyway, so these index entries are very long. The entire index is far too big to be stored on one machine. Instead, it gets divided over many, many, many servers. And each of those servers holds some set of the entries and the page reference. So what it looks like, right? Basically, you have, number one, the entire index encompassing all languages and all their search terms, divided up globally over, now we checked, we said over 21 data centers. Okay, and for all I know, there might be more than that now. They might have put in an extra one since that was written. So I'm going to say 21 plus data centers. Okay. Each data center has thousands of servers, index servers, let's be specific, that each hold a relevant segment of the index. Okay, so basically they're going to hold terms that have come up in that area. Okay, now that segment is going to be very, very, very large. If you think about each index entry, okay, each index entry is essentially as a key field, the term itself, and then the data, right, or the value. If you say this is like a key value thing, basically a long or very long list of page references. Basically where Google can find the relevant page data in another system. Okay, so that's, each entry is basically a long list of references of here's where that page is. So that's it. That's the index. Now, there's one thing that needs to be mentioned for semantics, right? For semantic terms, semantically equivalent terms, basically another key that points to the base key field. Okay, so for example, if you have two truly equivalent terms, right, then the first one is going to have its own long list, and then any other ones that mean the same thing are basically going to say, oh, you can find what you're looking for under this term. Okay, so I'll say, or for semantically equivalent terms might point to, you know, the same meaning key field. All right, so that's what the index entries are. Basically, a search term and then a long list of references. Now, we talked about this before. Queries that aren't in the local language are going to be forwarded to a different cluster, right? Somebody's going to look, Google's going to look at the index and say, oh, this thing that I'm looking for, this search term, is not contained locally. I'm going to pass this on to, you know, another server or to another data center. So each server holds a subset of entries and page references. Let's talk about how that works. So within a data center, you have groups of servers called tiers, right? And each group of servers contains some portion of the index, right? So say tier 1 basically holds segment 1, and likewise tier 2 holds segment 2, and likewise tier n holds segment n, right? And forever how many ... and so on until, right? You have many tiers, each holding a portion of the index. Now, the nice thing about this is Google wants to achieve a couple things. Let's talk. So first of all, I'm going to shrink this a bit. Okay. Google wants to balance two goals in providing fast search results, right? So it wants to deliver the results quickly, but number one, if every search query has to consider every part of the index, right, or every server holding part of the index, that will slow things down, right? So you don't want to have it do that way. It's going to slow things down by reducing system capacity. It's only going to be able to process so many queries per second, and so if you have every machine involved in every search, that's going to put a definite low cap on the number of searches per second Google can handle, right? Another thing, if a search requires a long list of data to be analyzed, that will also slow things down, okay? Because a long list is going to take longer than a short list, right? When you're when the work is parallel. So basically what you would like to do is have some kind of balance between those tools. You want to use a reasonable number of servers, okay? You want to use a reasonable number of servers so that no one server has to dig through a very long list, but likewise, you don't want to use too many servers because that will lower the overall system capacity to deliver search results. So these are the two problems that Google is basically trying to balance out, right? Does this work in parallel? The more machines it can involve, it can return the results faster, but the more machines it involves, guess what? It's going to be occupying more machines out of the system. So there's kind of a trade-off going on there. So first thing, right, once Google figures out which index entries correspond to the search terms, then it's going to forward that query to the appropriate servers, right, the servers that have that relevant data. Now, Google doesn't reveal its precise system details. However, one of the more interesting things, if you feel like digging through it, is patent documents. Patent documents are generally publicly available. Once the patent has been issued, then Google tells you all about it. Problem is, these are very long and legalese and hard to read. So, but if you scan around through it, you can get the idea, wow, this is a pretty long document. Okay, what all is going on in here? Well, this is query scheduling using hierarchical tiers of index servers. Yeah, that sounds complicated, and it is. But if we dig through it a little bit, we can find a few things. So here's one. I'm going to save you a lot of trouble. So this part here that I'm highlighting, suppose a user enters the query New York restaurants. Okay, that could have multiple meanings, right? Could have multiple meanings, or if you like, groupings of search terms. So it could mean restaurants that are new and located in York, right? There's a York, Pennsylvania, probably some others in the United States, and a York in the UK. It's also a fairly major city. So that's one possibility. Of course, more likely, restaurants located in New York City. Sure, that's possible. Or restaurants located in New York State, right? So there are different possibilities for how these could be arranged. Now, again, Google doesn't know what these terms mean. All Google can do, Google doesn't really understand word meaning, but it does track what users click on. Okay, so if Google observes that New York, for example, is a more important weighting, right? A more important weighting grouping, let's say, grouping of the terms than York restaurants, because A, many more pages have the combo New York, and B, many more users click on those pages. Okay, then Google can figure out, Google can begin to understand, or at least return appropriate results. Okay, so that's the gist of what they're doing. So there are many possibilities for grouping these terms together. At first, Google's going to emphasize the fact that users enter them in a certain order. So New York and York restaurants will be considered more valid groupings than, say, backwards, like restaurants York and York New. Google's going to basically figure people enter in the words in the same way they're going to appear on the pages. Now, if we scroll a little bit more through the patent document, we can find some more stuff, right? They talk in some detail about how the phrasification happens. That's actually the word they use, right? When they do all the query parsing and break it up, they have a whole sequence for how the points are awarded, right? So for example, here they have the sequence, quick brown fox jumped over the lazy dog. They have points awarded for the occurrence. They have points awarded for whether it appears in the body or in a header or in the title. They have what else? Something, whether it's final, right? Here is a little bit different, jumps over the lazy god. Anyway, basically the way the terms are arranged on the page matters, and is going to determine how well the search results are ranked. So consequently, so if we have something like this, the quick brown fox jumped over the lazy dog, okay, we might find that a page containing, depending on how the point system is implemented, page containing the quick brown fox, but no other terms, might outrank a page containing all terms in random order and not consecutively. Okay, so the point of this, there are a whole lot of different ways that this sequence could be ordered, right? It's a fairly long set of search terms. Now, if I find an exact match with this phrase, that's great. That's going to rank pretty high, all else equal. But it's not the only, many pages are not going to have all of these search terms, or they're not going to have them all in the same order. Google still wants to return something because it might be the right thing. Okay. So that's basically it. That's and again, if you want to dig through this, you can dig in painful detail through all this. They have a similar example like New York Ethiopian restaurants. So yeah, they talk about the phrasification for that, different ways that you could combine it. There are a lot of different options. Okay, so what Google's doing is basically providing a patent on how that sort of query parsing happens and the ranking process for it, but it's pretty complicated. Okay, so that's it. Search queries decomposed into likely phrases to address the large number of possible combinations. Now, a big thing, the documents are cleverly distributed over the servers. This is it. Number one, the server cluster is divided into segments so that each phrase entry is confined to one segment. That's not tricky to do, right? So, pile back into my picture a little bit. This part, this is easy to do. You divide your server into segments. Each segment holds a particular set of index entries, right? That's pretty easy to understand. However, this next part, mathematical function used to divide the entry list and assign documents to servers independently of the phrase. What does that mean? Well, every document is going to be assigned to a particular server, and what they want to do, I'm going to shrink this again. Remember, Google wants to avoid involving every server in a search. Okay, best option, confine related pages to a single server. That's the best thing it can do. If it has all the pages that might be involved with some single search, it wants to confine them to a single server, so it only has to consider that one server for resolving the search. Okay, that's the best option that Google has. So part of the way it does that, right? We look at the phrasing here. Function used to divide entry list, assign documents to servers independently of the phrase, right? So each document will exist on one machine. And any search query that references that document, right? Because the document contains a term in the query. Okay, any search query that references the document will find it in the same place. Okay, so you have a whole bunch of different sets of search terms, right? But they're going to be grouped in a way so that every search that might turn up a particular document is going to point to that one particular setup. It's not that hard to do, but they're going to group essentially the portions of the index that reference the same pages will be located as far as possible on the same servers. Okay, so that's the idea, is that you don't want to involve too many different machines in the operation. This is kind of a complicated thing. It's a little bit technical. I'm not going to really ask deep questions about this on the exam. So, I have a picture here. So each index gets divided into n sections, gets divided to server tiers. Each index entry is distributed over one or more shards, basically portions of the tier, so different machines within that tier. And it's put on separate servers so they can do it all in parallel, right? So if you're trying to read through the index to retrieve all the pages, well, it's going to happen faster if that's running through multiple machines instead of having that one big long list of billions of terms on one machine. Then there's an assignment function to ensure that a given page gets stored in the same shard for any entry, including the page. Well, what that means is just if there's a search that's looking for a page, it's going to find it in the same place, right? So all that means, all the pages that are going to be involved in a search, they're all going to be in one place. So Google's not going to have to search through all of its servers when it's digging up this data. Okay, so the indexing system, the big picture on all this, again, Google wants to provide necessary parallel operations to process search queries quickly, but only wants to use the minimum number of relevant machines. Okay, and it does that achieved by grouping index segments and web page data, okay, into small sets of, into small sets that are used together. So the idea basically, instead of having a little bit on every machine, right, in a bunch of different places, what Google would like to do, right, so we have a little bit on every machine in the system. No, we don't want to, or in like multiple tiers within each data center. Google doesn't really want to do that, right? Google says, yeah, we got to do some parallelism, but first of all, what they're going to do, as far as possible, they're going to combine into one shard, right, one tier, what it's going to do, and then some small set related machines within that tier is where the information is going to be. And essentially, this is like having separate pipelines for processing each query. That's the end goal. A set of parallel pipelines for processing the query and returning the results. So to the extent that Google can say, this is what I need to use, I'm going to have it run in parallel, but I'm going to try to have it not trip over a lot of other stuff that's going on elsewhere in the system. That's going to allow Google to both process queries quickly and have high capacity. Okay. So moving on. Next thing, document servers. So of course, Google stores tens of trillions of page documents. Essentially, for every copy of the, Google basically has a copy of the surface internet, and it has to have multiple copies of each in case something happens to them. Now, because document objects don't have a definite structure, right? We've talked about that. They have to be stored in a separate system. It would be kind of horrible if every time Google did a query, right? Somebody enters a query into Google, Google would have to dig through its entire stash of web page documents and check through all of them and see if the terms are there. No, it's horrible. Google just says, has a database that contains data about what the web pages have, but it still wants to keep these raw documents in case it wants to modify its algorithms, run tests, verify that changes to the page have actually happened, and see if the pages are significant, right? If this is just an image being changed or something very big that's changing the text and thus requires Google to make changes to its index. So all that, that's why Google keeps the documents. So anytime a query gets processed by the indexing system, right, Google doesn't use the raw documents. Instead, all of the documents are pre-processed. For example, what the users get, a blurb of text, typically the title and the first few lines, and then a whole set of literally hundreds of relevant variables for each document that Google uses to determine how the page should rank. And of course, there's going to be multiple rounds of page ranking. So for one, before Google looks at the document, it's going to simply recover the search term match strength, right? Are these terms contained in the document at all? And then afterwards, Google can pick through and try to find, are these terms included in the same order? That's an issue as well. Okay. Now, as far as any outsiders know, right, Google, again, is not really forthcoming on the special sauce of their system. As far as anybody knows, Google uses a single methodology for page analysis. And what it does, takes this raw web page data and reduces it to a set of variables. So one, there's the title and the blurb, right, the text right under the title, and then hundreds and hundreds of other factors. For example, when the page was made, whether it contains images or not, what it links to, all sorts of stuff. Now, as far as we know, again, there's a uniform structure to this. So for any page, it's going to get processed to look at the same set of variables. And because there's this uniform structure, it's generally compatible with relational database systems. And of course, documents also stored in their original form. Now, how do they get stored for ranking? Well, Google has a system called Bigtable. Bigtable is their objects are stored as sparsely populated tables of rows and columns with a timestamp. So it's a different structure. Let's talk about this. Okay. So Bigtable is basically Google's system database for holding web page data. Okay. Now, why do we need this? Well, if you had an ordinary relational database, you would have a large set of fields, right? So for example, a web page might contain dozens or even hundreds of images, okay? In a normal relational database, every row would need to accommodate the largest possible number of images, right? Same thing for any data that might occur in multiples, right? So that's one problem right there, because most web pages aren't going to have, say, 1,000 images. But if Google wants to store all these images for a web page, yeah, it has to keep room for 1,000 of them. Okay, or even if it's going to cap it off at 10 or 20 and just keep, some subset of them, still it's going to have to provide that for all the documents. There's going to be a lot of zeros. Second, Google looks at several hundred web page variables, but many or most will not be relevant to a particular page. Okay. That means effectively they'll contain zeros. Or they'll be empty. They won't have any real data. And all that means wasted space in the database. Okay? If you have a lot of pages that have reserved fields, but those fields are empty, well, again, lots of wasted space, lots, not lost, lots of wasted space, meaning more expenses around storage media, and longer search times, right? Because it has to scan through all these rows even though there's nothing there. So this is all a problem that Google has to deal with, and it does it by having Bigtable. So Bigtable, the key things. Number one, a row can have columns that are groups, right? Basically, pointers to lists of data. So for example, if a record has an image set field, that can link to a list of many images, but otherwise doesn't take up extra space in the database. So that's one thing. You can have these what are called families in your columns. Number two, the database is designed to accommodate sequences of empty fields at minimal storage cost. In essence, right, when a large set of empty fields occurs, the row will just have a column group that is zeroed out, right? That is it's basically marked skip these columns because there's nothing there. In essence, that's what happens. So those are the two big things in Bigtable, and the technical terms for that, right? Column families, that's one. That's, you can have groups of data of the same type. And the other, sparsely populated. Columns may be empty, and empty entries require virtually no storage space. Because why? Because Google has some pointer that says, there's nothing in this set of columns. Other thing, groups of related rows are stored near each other. So this isn't not an inherent feature of the database, but we'll say Google also arranges the data within the database so that rows that are used together are located near each other. Okay, and this solves the problem, or it's designed to solve the problem. Again, means that Google doesn't have to search a lot of different machines or, different locations on one machine to find what it's looking for. Meaning queries and updates can all happen faster. Okay, this is analogous to how Facebook stores images in albums, because the grouping makes them quicker to retrieve, right? Same kind of idea. So Bigtable has these three features. It's like a relational database, but has extended features and capabilities. So it's not really a relational database, but in some ways it can act like one. It's just specialized for what Google needs. All right, last thing, spelling servers. So spelling servers are pretty easy to understand. So when you enter a search into Google, the spelling server receives the original search query. And the way it wants to identify whether words are misspelled, basically it looks at two things. Receive original query string, then looks to see if any terms or term groups are, number one, extremely unusual, and very similar to common terms. Okay, and that's how you recognize a misspelling. If so, indicates probable misspelling. Right? That's what a misspelling is. You typically enter in something that is close to something, but not quite. Now, you can have fun with this. You can go to Google and enter in some oddball strings. For example, I could do something like univ of illa, okay? And Google, let's see what they do with that. Wow, it actually popped in. Oh, shit. I didn't mean to do that. I didn't mean to actually show up something, but apparently andoc is a very popular thing. Let's pull out these numbers. There we go. I can do something screwy there, and it says, well, you know what, universe, Illinois, that's the closest that they're going to get, right? So it shows you that. It can do pretty good guessing, if you, especially if you start with the same stuff. Let's try if I do it without the I. Oh, nothing. I got nothing. All right, that's kind of fun. Okay. Anyway, it's an interesting thing to test, you know, how badly you can spell things and still have Google say, yeah, I think this is what you're talking about. Okay. So, interesting thing, Google had something called the Google Search Appliances. They don't exist anymore, or I mean, they exist, but Google doesn't service them anymore. I'll show you what those were. The idea with the search appliances, if you look at that, it's that yellow thing on the podium there, is basically a server type machine for document storage. Now, the problem with document storage is that words are not always typed in correctly, right? And the question is, if you type in a document and you say misspell the author's name or have some important misspelling in the document, it might be impossible to find. And that's a serious problem. So Google developed this technology and included it on its Google Search Appliance for businesses could index up to 10 million documents. It was a very, very nice thing for that. But again, it's kind of a machine. Google, since they've gone to cloud, they want everybody to join Google's cloud service, and they're not really servicing these appliances anymore. But that's another way where these spelling issues were resolved, so that people could find their documents even if something was misspelled on it. Okay. Now again, for over 10 years, Google has corrected user spelling. Sometimes it's an actual definite error, right? So if it's a search term that has no index entry or very few matches, Google can see that and say, yeah, that's not something that we've seen before. But sometimes you can type in a correct but unusual word that are very popular, similar to popular search terms. So sometimes Google guesses wrong, but you know, you might actually mean what you're looking for, but Google thinks, wow, this other thing is really popular. Are you sure you aren't looking for that instead? Now, how the spell correction process works, number one, there's a query rank. So for a term that has a high frequency, that is, it occurs a lot, and it's rarely revised, that means that once somebody enters the query, they accept the search results and go onward. They don't type in the query and then see the results and say, oh, I didn't mean that, and I try it with some different words. That's what revision is. So if a query has high frequency and is rarely revised, then Google's going to say, oh, yeah, this is probably what you meant. That's great. However, if there's something that has a low query rank, right, doesn't occur very often, and it is or frequently revised, and it's similar to a high-ranked query, then Google's going to say, you know what, on the balance of probabilities, it's more likely that you typed in something wrong than that you entered in this oddball query. So we're going to try giving you, you know, what we think are the correct results. And this similarity can be applied to individual words, semantic units, which could be groups of words, or simply observed from sequential searches, right? So the revision process, if I type in something like, let's see here. If I do something stupid like 2 R's for Ethernet, right? Google's gonna say, oh yeah, I'm gonna give you Ethernet, right? I'm not gonna give you Ethernet with 2 R's. But if I really want to see Ethernet with 2 R's, I can say, nope, that's what I meant. And I say, oh no, surprisingly, I got 5,000 results. That's interesting. There's a fair number of typos out here. So here's one, Ethernet. Hilarious. Ethernet. They're out there. What can you say? Okay. Go back. All right. Last slide. Good, we're right on time. Indexing troubles. So one issue that you might wonder, how does Google update the index given that Google is running worldwide with billions of searchers doing it? Well, first of all, as far as Google users are concerned, any pages, any search results, they're read-only, right? Ordinary users can't go into Google and update the contents of Google's index. So that's one thing. Google doesn't have to worry about simultaneous access in that sense. So it can provide access to a lot of things. Second, the system itself is designed to allow small-scale isolated updates quickly, right? So we talk about Bigtable a couple slides back. Groups of related rows are stored near each other, so queries don't search the whole database. So anytime there are updates going on, Google can just pinpoint that portion of the Bigtable database. It doesn't have to run through and update the whole thing with a big batch. Third, duplicate copies are maintained locally, right? So at any data center, if Google has one copy of the page data or the index using it, then guess what? There's going to be other copies available. Google always wants to keep a triple copy. So at least one page copy will always be available. If Google is updating one, the other two will be available. Now, for search results, this means that there's sometimes a policy of eventual consistency. So while something is being updated, different users might receive slightly different results for the same search query, right? So for example, if you have 3 copies of the data and user 1 enters a query, then user 2 enters a query, what might happen, these 2 queries are entered at the same time. We'll say for whatever reason, these 2 copies are unavailable. They're on machines that are doing something else, right? You might have user 1 enters the query, then immediately afterward, boom, the update happens. Then user 2 enters the same query and sees the different one. Or it could be that at some point you have one of these has been changed, one of these hasn't, and depending on, which device you get connected to run it, right, you might get one or the other because this one might still be waiting for something else going on. So anyway, it is possible that users might get slightly different search results while this data is being updated. However, this is a read-only system. It's not a transaction processing system, and search results are inherently a little bit imprecise. So some imperfection is expected, and so some inconsistency is acceptable. Basically, the changes that happen to a page, typically, you're unlikely to cross paths with them at any given moment in time, right? It's going to take a few seconds to update any one of these entries. Number 2, the possibility that you actually get different data is pretty low, even if the things are getting updated. Google's going to try to, direct you to the one that's available. So it also depends on what other people in the universe are doing. And then number 3, even if something is inconsistent, the costs of that inconsistency are pretty low. So Google's made this trade-off for eventual consistency, just like Facebook. Perfect database consistency would slow down search results too much. Basically, if anytime Google did an update, it had to insist that all of the copies of the data had been properly updated before any of the machines involved in that update could be used to respond to search queries. Then it would slow down the machines, right? It would slow down the system, and Google wouldn't want that. Basically, every now and then you'd have some search query that might take 10 or 15 seconds to get processed. Google doesn't want to do that. All right. So that's it. That's indexing and retrieval. Now, I guess we have a minute if anybody has some questions they want to ask about stuff, but we can always come back during the review section and address some of these things. All right. Are we good? We're good enough? Good enough. Okay.